Hello, warm welcome from Framos to today's webinar. Today we're going to have a very exciting topic, 8K imaging, considerations at the system level, designing your complete 8K vision system from sensor to stream. The speaker today will be Giuseppe Contini. In the next half hour, we're going to learn about the challenges that people are typically facing when building an 8K imaging system. We're going to look into use cases, what it actually takes to build an 8K imaging pipeline. And then towards the end, we'll also learn about how Framos supports their customers on the journey. And last but not least, we will have 5 minutes towards the end dedicated to questions and answers. My name is Frederik Schönebeck. I'm the Director of Growth, and it's my pleasure to introduce to you today's speaker, Giuseppe Contini, the technical imaging expert at Framos. He is a computer science engineer by training with over 2 decades of experience in imaging system software and hardware. He's been with Framos for more than 7 years, and he has supported numerous customers in all kinds of different applications by providing custom design solutions from requirements to production. He's very dedicated to research and development and is always trying to push the boundaries of the field of imaging. As a technical imaging expert, he continues to drive innovation and contribute significantly to the growth of the field of computer vision technology, and more importantly, to the community where I count us all in. The way to ask questions is by pressing a certain button towards typically the upper right corner of the applications. So if you have questions, please hit this button, type in your questions, and we will get back to you either at the end of the meeting if time allows, or we'll follow up offline. With that said, I hand over to Pino. Looking forward to a great webinar.
Thank you, Frederick. A very nice introduction of me. And yeah, Pino Giuseppe, it's me, it's from Italian. And I will be starting talking about challenges from our experience, because we also go into this. And I want to give you some perspective, as the title of this webinar is at the system level. So first of all, here it's a diagram. I want to say that 8K is not just more pixel. I think that this is the starting point of the discussion today. So 8K means 8,000 columns at 60 frames per second. At bare minimum, you have 2 main topics. One is huge amount of data, and the other one is the size of the pixels means bigger image sensor or smaller package, smaller pixel size. So this goes into the high pixel density, to the packaging topic. It could be bird eye. And then if you have very small pixels, means that you have very high MTF or very high spatial resolution. And then you have low saturation and low sensitivity because the pixel size is very small. And so you see how this most of the time we see, and we will see an example, some different color filter array there. That means that you need to do different kind of processing on the ISP. On the other side, you have a lot of data. Typically, you have 100 megapixels to be processed between in the frame rate time, so typically 10, 15 milliseconds. And then you have the interface, MIPI, D5, C5, SLD, SEC, and this means also a very powerful processing side. So this is what just changing the number of pixels from 4K to 8K means 4 times the resolution opens all of these cascade topics to be managed at the system level. First, image sensor, size matters. What is 8K first, or 4K? Typically, we refer to TV resolution, and 8K is in the range of 7,600 80 pixels, but in general, we can say simply 33 megapixel. And typically you have 30 frames per second or even 60 frames per second. Now everyone wants to have very high frequencies on their TV. And so this means that you also need to acquire this data. You need a camera to catch this data. And so just moving from 4K to 8K, I mentioned before, you have 4 times the resolution because we are talking about a rectangle. So we talk about an area. And so the area is 4 times. What we have on the market, there are some sensors. We are very close to Sony, and mainly they produce some very nice sensor. But here I want to give you an overview on trade-off: image sensor format and resolution. Of course, because you have so many pixels, means that the sensor size grows in dimension. And so these are the typical DSLR camera where you have a full frame format or over 1 inch format. So it means quite big sensor. Means also a lot of money because this is mostly, I like this rule of thumbs. The sensor price is per square meter, like a house that you can buy in Rome, in Munich, or in Tokyo. So here you have a IMX 455. This is very nice, very nice image sensor. It's even more than 8K, 61 megapixel, but it's 43 millimeter. So here you have the size of the pixel, they are scaled. Sorry, the size of the image sensor, they are scaled here, and you can see how big is this guy. So this means a very expensive system, very big lens, typically F mount or even more, or if you are lucky, C mount. So going down into the sides, and also we are seeing a lot of new applications that are requiring 8K because of maybe digital zooming or because they want to do streaming on the web 8K, but this could not be thousands of euro just for the sensor or for the system. So in this range, below 1 inch, you have some pixels. They are very interesting. For example, I selected 2 of those. IMX 06A and 586. So it's 8,000, 48 megapixel, or 8,000 again, it's 50 megapixel, a bit wider at 30 frames per second. And here you see the size, the physical size compared to the full format, more or less image sensor. You also have 283, but yes, in general, you have to deal with the size of the sensor and the cost. Now, what means a small pixel size? Small sensor means a small pixel size. 586 comes with 0.8 micrometer per pixel. And this is very small pixel size. Means very low light sensitivity, and it means lower saturation. The bucket is smaller, and as consequence, a lower dynamic range. And most of the time, this also comes with some special filter array. Here you see quad Bayer, which is non-common because typically we see red, green, blue, but here we have 4 reds, 4 green, 4 blue. So here the real size of the color pixel is 4 times. And also, many times you have this is a very, very small. You see how small is this guy? And this is available as a bird eye. So this is a sensor board, a drawing of it, and there's no package compared to some typical situation where you have the package. And just this is a huge difference because, of course, you have to do wire bonding. This means you have to have a contract manufacturer. This is not very easy to manage, and there are tooling costs, quantities, and so on and so forth. So you see how this small pixels deals to a lot of new topic that needs to be managed. The IMX 06A is nicer. It's a bit bigger pixel size. Actually, it's 2 times. Still comes with quad Bayer. It could be available as a packaged sensor, so it's a good compromise. But this is still 1 inch, so it is still a challenge because means a bigger lens, so it's not M12 domain anymore, and so on. Data rate, I mentioned that. Here is a comparison. On these straight lines tells you how fast could be the interface by specification. So D5, this is the very common one, D5 version 1.2. This is 2.5 gigabits per lane. 4 lanes means more or less 10 gigabits of bandwidth here. And with 10 gigabits, you can stream, of course, 4K, but already if you want to go on 8K, 30 frames per second, the amount of data that the sensor is producing is bigger than the bandwidth of the interface. So it means that you have to look at different interface, and C5, for example, or still the D5 is there is a version that allows you up to 12 more or less gigabit, 18 gigabit per lane. So you have this again and a trade-off between the interface and the data rate. So the payload is high and means that you need to have some powerful receiver that is capable and have the right interface. Not only, for example, just selecting C5, with which is faster than D5, then this is a trio, so it's not a pair of wires, but it's 3 wires. And here is an example. You have to match the impedance between the lines, but just because you have 3 lines instead of 2, then you have some layout routing, PCB routing topic that needs to be managed. So this increases the PCB design complexity. Optics. So I mentioned MTF resolution. Here is a typical lens modulation transfer function of a lens. You buy a lens, and this is a low-pass filter. A lens, it's a low-pass filter, but actually you have very high data to manage because you have a very small pixel size, and so you have very high frequencies. Here you have the frequencies, and typically the lens at high frequencies goes low. And here means that you need to have a very high quality lens, say that. And so here you see 600 cycle per millimeter if you want to run 0.8 megapixel, or this is the Nyquist sensor, the Nyquist frequency of the sensor. The lens should match the MTF of the sensor. Again, the circle of confusion, the spot on the sensor should be 2 times bigger than the pixel, or should be within 2 pixels. This means that because the pixel is very small, the size of the spot means should be very small. What means this translated into the optics? Is very likely this system is diffraction limited. Because the f-stop should be very small in order to be able to have this small circle of confusion. I give you an example here. Typically, f-stop is less than 1 for 0.8 pixel size. Of course, you can go over, but means that you have some bigger pixel size here, and means that you are running then into lower contrast here, because of course you spread the incoming ray over several pixels and you are not capable to catch fine details. Of course, this is quite simple, but most of the time it's forget. So with the smaller pixel, if you want to keep the same field of view, you need a shorter focal length. And this moves the topic to the fisheye domain, because the typical focal length in this domain is 1 or 3 millimeter, where you have a very high distortion, or fisheye distortion is not more f tan theta, is not more proportional, but is f theta or fisheye theta. And many algorithms to do undistortion, they are based on f tan theta, so on the proportional distortion. So this is another topic to be considered, right? That being said, multi-pixel configuration. This is also interesting situation that you can find on very small pixel size, where you have, for example, here to do digitally recover RGB pixel structure. Or you have to deal with binning at the 4 pixel level, or you could have HDR, high dynamic range, where the pixels are used in a different way, where you have low exposure, medium, and short exposure. And so that means that you need to have a dedicated ISP or an ISP that is capable to do this. Not only some remosaicing here we have experience, and you see the colors in this image is moving a bit between the red and the normal. You see kind of aliasing of the colors. And this is a 50 megapixel. I cannot show here the full picture, but if you look, there are even some artifacts in the image. And of course, this is something that needs to be managed on ISP and tuning level. So, use case. Okay, what we did, and this is a concrete case, 8K prototype with 586 image sensor. You see the wire bonding that we did here. You see the sensor board with the sensor itself bounded on the sensor board, and you see here the NVIDIA. This is an NVIDIA IGX Xavier with a Framo sensor module connected and streaming with the lens. Not only, we also solved the topic of the tuning. You remember these pictures coming from the previous challenges. And now here, after deep tuning, say that, you see the colors are the red ghost is gone here, and also you don't have the artifacts anymore. So this is a concrete case that we have, and we have recognized and solved as a tuning. So on-chip tuning, aliasing and artifact, color aliasing, sorry, and white balance compensation due to this red ghost here. This is also a comparison. So, okay, compared to, because we have for a quad buyer, one could say, okay, but this is like a 12 megapixel. So it's not 8K, but is 12 megapixel. And indeed, we have a comparison here. This is a quick and easy way to compare. Is a test chart, IMX 678 with 4K. And this is 586 with 8,000. So this is the image compared. And this is a resolution test chart where you can see here the contrast at this point is recognizable. But if you compare here, the contrast for the 586 is almost the same, but at different and much higher frequencies. So we can catch much more details. So you see how Framos not only investigate the challenges, not only do prototypes, but also is going into investigate and make available some pre-validated 8K stacks, something that you can use or you can buy for testing, or you can in some way use to as a starting point for co-design, where can be done together. Here is IMX 06A, so it's again 8K modules with driver and ISP, and also prototype and production quality validation, because also item to items variation is very important in this case. So we talk about a sensor board with a packaged image sensor, high precision lens holder, and high resolution lens paired to the sensor. Regarding the interface, we consider to use our PixelMate connector and provide MIPI C5 and D5 interface that could be connected to NVIDIA, Qualcomm, and other platforms that support that, right? So this is mainly the good and short presentation on this. So I see we have 10 minutes more for question and answer. I don't know if Frederick would also say and comment something about some stocks and our experience on this, but I left the stage to the audience for questions.
Thank you, Giuseppe. A great overview. Yes, I can relate to all the things you have highlighted. It is a journey that one needs to go through, and there is challenges along this journey. So we have received a couple of questions. One is regarding frame rates. You mentioned that different standards, different protocols have different speed limitations. Can you translate this into achievable typical frame rates? So with the DeFi that was mentioned, MIPI DeFi standard, and a typical resolution of 8K, what is a typical frame rate you can get?
Good, indeed. This is in some way a simple math. The D5, you have now mainly two versions. 1.2, which is 2.5 gigabit per second, 4 lanes. So this is the bandwidth of the interface. Or you could have a MIPI D5 2.1, which is 4.5 gigabit per second per lane, always 4 lanes. So if that is the bandwidth of your transmission channel, then the amount of data that is generated must fit into this bandwidth. And so translated into frame per second, this is more or less 22 frame per second if you have MIPI D5 1.2. And okay, quick math is more or less 35 frame per second if you have D5 2.1 at 4.5 gigabit per second. So this could be seen in the in some way in the slides here. I want to maybe take the chance to recall this slide. So here you have MIPI D5 1.2. So this is the very common now. And indeed, the 8K 30 frame per second, it's a bit more than the maximum that you can get on D5. And so indeed, this is in line with my estimation is about 20 to 25 frame per second. But if you have powerful interface, what means powerful interface? You need to have a host, a receiver that is compliant to 2.5, that is capable to receive 4.5 gigabit per lane. So in this case, you have here 8K, and so you have a bit more bandwidth here. So indeed, with my estimation, you can go, if this is the blue pillar is 30 frames per second, then you can go over up to 35 frames per second. Yeah. So, but this is the math. It's very simple. The number of rows, columns, frame rate, bit depth, this also matters. And of course, a bit of overhead that you can assume is in the range of 20%.
Awesome. I think this does answer the question to full extent.
A lot of number, I know, but yeah.
There's a couple of questions on the optics. So you mentioned in your presentation the 06A 1-inch sensor. How about the chief-ray angle for that sensor? Are there any sort of exotic requirements on the lens that arise from chief-ray angle match?
A good question indeed. I did not mention CRA, but this is important things to consider. So let me use this drawing here. Most of the time, these sensors are designed with wide CRA because they are designed to stay very close to the lens. Like in mobile phone application, you have a very compact design. So it could be that some sensor has a CRA in the order of 30 degrees. And so this means that you need to have a lens that is matching this CRA. So actually the micro lenses on top of the pixel are shifted in a way to catch wide angle coming from the scene. So the best would be if you have a lens that is matching the sensor CRA, and 30 degrees is quite a lot. There are some lenses that could be closer to that, in special M12 lens, or there are variants of the sensor that comes with smaller CRA in the range of 10 degrees. And in this case, you have a very good chance to find a lens M12, for example, with the matched CRA. For IMX 06A, is the same, but because the pixel is wider, then the lens are in the range of it's bigger than M12 because the sensor is 1 inch, and actually there you can easily find, it's easier to find a matching in terms of CRA. If you don't match the CRA, then you have a much higher shading at the corner mainly. And if the mismatch is too high, then you can have kind of crosstalk because then the light goes into a neighbor pixel instead to go into the pixel that should go. But yeah, this is tricky but manageable. And it's important to keep in mind. Yeah.
If I understand, there's good news. 06A is available in a low CRA version where it can be paired with more, let's say, available and off-the-shelf lenses. That's good news. Okay.
Right.
There's actually a second part to the question, which is how can I get early access to this module, to this camera module that you described. So I think to give the answer right away, the short version is when you're already in contact with Framos, just let us know through your main point of contact. If you're not, you can always reach out to us through our website or through our regular support@framos.com email address. Giuseppe, there's time for one last question, which is
Please.
on the demosaicing. You mentioned that there can be artifacts that you need to control, otherwise they result in bad image quality. So the question is it really necessary to do this deep IQ tuning that you mentioned to fully get rid of those artifacts? Because typically there should be classical demosaicing algorithms available in the community, which usually don't result in those artifacts.
Demosaicing, yes, but here we talk about remosaicing. So the artifact comes when you go from quad Bayer to a full standard Bayer. So the goal is to really have, because if you go in this way, you have actually 4 pixels. So the true resolution is 1/4. So if you have a 48 megapixel here, you have 12 megapixel of true resolution. So what happens is that you have to have the full resolution at a 48 megapixel, you have first to convert these 4 pixels into one standard RGB pattern. So this is remosaicing. It's the reverse of mosaicing. And so, and then the output here, you have to do the standard demosaicing. So in this process, you have some aliasing and some artifact that could appear when you go from quad Bayer to standard RGB. And because of that, you need to do this deep tuning to avoid that aliasing happens at this stage. Most of the time, this is maybe not on the ISP, but is on the chip itself, so on the sensor, because it knows very well how to manage the signals and how the pixels are combined together. So there is a correlation of the noise, a correlation between the pixel inside of the circuitry that can be used to do a proper filtering. So mainly deep tuning means do the tuning on the chip and enable the host ISP to communicate information to the chip in a way that to know the white balance and so on and so forth. So it's a combined tuning that I call it deep tuning.
Okay, I think that made it clear. We are now 1 minute over time. Let's wrap up here. Thanks a lot for the great presentation. Thank you for all the interested questions. For any questions that we have not been able to address, we'll reach out. And with that, thanks for your attention and see you at our next webinar, which will be on HDR imaging and is scheduled on November 4th. Thank you. Bye-bye.
Thank you. Bye-bye.